Continue our discussion of system of equations. So remember that a solution to a system of equations are values, plural, of the variables that make all the equations true. So for example, if we had this system of equations, 2x plus y equals 7 and x minus y equals 2, that has the solution x equals 3, y equals 1. And we can write that solution as the ordered pair 3, comma 1. Now, if we're dealing with the variables x and y, we always write the x first and the y second, okay? I mean, 99.9% of the time. You will always write the x first and the y second. If you're dealing with variables, say like r and s, usually if we're going to write them as an ordered pair, we write them in alphabetical order. But you don't have to. You would just need to specify what order that you were using if you have variables other than x and y. We've also learned that to verify a solution is the solution for a system. We just want to plug those values in to each equation and verify that it makes a true statement, okay? So we just plug in the values and show that it's a true statement. Now these numbers 7 and 7 are not necessarily going to equal these numbers over here 2 and 2. That's not really what we're showing. We're just showing that if x is 3 and y is 1, that's a point on this line. It's a solution to this equation. This equation has a whole set of solutions that are totally different from this equation. But they have one solution in common in this case, and that solution is 3, comma 1. So what we want to do in this activity is verify solutions. Try to determine if something is a solution. Question number 1, determine if 3, 4 is a solution to the system. So if it is a solution, then you're going to want to plug 3 in for x into both equations, 4 in for y, and if it is a solution, then both of these statements, these equations, should simplify to where the right-hand side is equal to the left-hand side for both equations. All right, let's check it out. So we're going to put 3 in for x and 4 in for y. 3 in for x and 4 in for y. This isn't looking very promising, is it? One more highlighting here. This is what we're doing. I can see that it's not looking good. This side's going to come out to be 13, and that does not equal 7. So the point 3, 4 is not on the line 2x plus y equals 7. And for the second equation, the left-hand side's -1, the right-hand side is 2. So 3, 4 is not a solution to the second equation, so it is not a solution to the system. It has to be both. Even if it would have worked with one equation and not the other, it still would not be a solution to the system. Or for the system, maybe that's a better way to say it. Anyway, okay, I want you to try 2 and 3, same idea. Pause the video, work those out, and unpause the video when you are done. All right, so for number 2, -1, 5 was not a solution to the first equation, but it was a solution to the second equation. Therefore, it is not a solution for the system. Has to be true for both. So graphically, what this would look like is you'd have the point -1, 5 on one of these lines, but not on the other line. Right, so you know, it might be something like this, where that point is on one of the lines, but not on the other line. Okay, the solution is going to be the point that's on both lines. All right, let's take a look at number 3. All right, this one looks good. The solution worked for both of these equations. So in this case, I think I would write the ordered pair as HC. Now, this is a good example of where I wouldn't put them in alphabetical order. Now, why is that? Well, I'm looking at this set of equations, and I'm kind of imagining a scenario here where H is hours and C is cost. Let's say this is somebody charging me for lawn work. Okay, so the first company is going to charge me $30 to show up and then $10 an hour. The second company is not going to have any initial charge to show up, but they're going to charge $12.50 per hour. So if I was graphing these, the hours would be my independent variable and the cost would be my dependent variable. And so the ordered pairs would look like HC. All right, so we could say 12,150 is a solution to this system. You could always write your solution also as, well, not always. If the directions say to write your solution as an ordered pair, then you need to do that. But you can write your solutions like that as well, just sort of listing the values. Okay, number 4 is an interesting question. Henry was looking at the system of equations x plus y equals 5 and x plus y equals 7. He said, just looking at the system, I can see it has no solution. If you add two numbers, that sum cannot be equal to two different numbers. Do you agree with Henry? So I want you to just pause the video and take a stand, write it down. Do you agree with Henry or not? Well, I'd be curious to get feedback on this. It's hard to do that in a video. But he seems to be onto something. I mean, you're trying to find some values for x and y that you could plug in here and have it come out to be 5, and then pick the exact same numbers and have it come out to be 7. That's going to be pretty tough. Probably not going to happen. Let's think about this graphically for just a second. We could even go to Desmos and graph these and look at it. Let's put in our two equations, x plus y equals 5 and x plus y equals 7. Where are those lines going to cross? They aren't, right? They're never going to cross. So it is possible for a system of equations to have no solution. If we think about this geometrically, if we're dealing with two lines, now if the graphs aren't lines, all bets are off here, but if we're dealing with two lines, they're either going to be parallel, like we see here, which is no solution, or they're going to cross, like we saw in our previous activities. Or it's possible they're the same line, which is a little bit weird, but like if I had an equation where I just took the first equation and multiplied everything by 2, 2x plus 2y equals 10, well, these are basically the same line. They're just right on top of each other. And they are considered a system. It's kind of a weird example, but all right, so Henry is correct. I want to say one more thing about this problem, another way to think about this. If we put these equations in slope-intercept form, y equals mx plus b form, and I subtracted the x over on both of these, the first equation would be y equals negative x plus 5, and the second equation would be y equals negative x plus 7. What are the slopes of these lines? Well, the slope of this line is negative 1. It's the number multiplied by the input variable. The slope of the other line is also negative 1. When you have the same slope, these lines are parallel. Pretty neat. Okay, so think about that. Let's think about change in y over change in x. Let's put this other one back in. Both of these lines have a slope of negative 1. So if I'm at some point on this black line, and I want to move off of it, to get back on it, I'm going to have to go down 1 over 1. That's my slope. Down 1 over 1. Down 1 over 1 to get back on the line. Same thing with the blue line. It has the same slope. Down 1 over 1. Down 1 over 1. So if you're doing that on both these lines and they have different y-intercepts, they're never going to cross each other. Hopefully that picture kind of helps with that. So if you see two lines that have the same slope, their system is going to have no solution, assuming they have different y-intercepts, which for you, most of the time, that will be. So let's just write that down and then we'll wrap this up. So if two lines have different y-intercepts and the same slope, then the system has no solution because the lines are parallel. Excellent.